I've recovered already, so yeah. So it's my pleasure to introduce Semyon Alesker from Tel-Aviv University, who is going to speak about, I've forgotten your title, I'm sorry. It was Valuations.
Geometric inequalities and valuation theory. Okay, thank you for inviting me to speak here. The goal of this talk is to remind, first of all, some background on from general convexity, more precisely mixed volumes, remind some classical inequalities for mixed volumes, which played an important role in development of the subject. Then I will state some new recent inequalities on mixed volumes. And then I will explain what kind of recent and not so recent developments stay behind these new inequalities. Developments for valuation theory, which has been my main area of research for many years. So at the beginning of the talk, I am going now to introduce or remind maybe for some people what mixed volumes are, but let me start with some notation. So we denote Rn the Euclidean standard Euclidean space of dimension. And we denote by script k of Rn the family of convex compact subsets of Rn and non-empty. Convex compact sets I will also call convex bodies, so it is the same. Let me remind you the definition of the Hausdorff metric on this family. Hausdorff metric. So how's the distance between two compact, let's say, convex sets? It is infimum of all positive epsilon, such that A is contained in epsilon neighborhood of B. This is a notation of epsilon neighborhood. And symmetrically, B is contained in epsilon neighborhood of A. It is a standard fact, and it's not hard to show that this is a Dieter metric, satisfies triangular inequality, etc. And I will also mention that family of all convex bodies equipped with the Hausdorff metric is locally compact space. It is so-called, it is consequence more precise of the Blyashky selection theorem. Okay, and one more piece of notation which I need to introduce mixed volumes. Minkowski sum of two sets. A plus B, which is just rather straightforward. It is set of sums, little a plus little b, little a belongs to A capital and little b belongs to B capital. And it is easy to see that Minkowski sum of two convex bodies is again a convex body. Okay. And now let me formulate the following non-trivial result of Minkowski.
I press you your yes. Yeah, I press. Thank you. He's a step ahead of me.
It says that let K1 Ks be convex compact sets. Then volume of the Minkowski sum lambda 1 K1 plus lambda S Ks is a polynomial in non-negative coefficients lambda 1, lambda s. So you just consider these positive homotopes of these convex bodies and take the Minkowski sum. Polynomial in lambdas, homogeneous of degree n. So homogeneity of degree n, it is immediate property of Lebesgue measure of volume, but polynomiality is a non-trivial statement. And the definition of mixed volume is based on this theorem. So let us give now definition of mixed volume. So let us take S number of bodies to be equal to the dimension. And consider this polynomial, lambda 1 k1 plus lambda n ks, kn. So it is a homogeneous polynomial in lambdas of degree n. So it contains monomial, in particular lambda 1, lambda n. So let's write it separately. Times certain coefficient, which I will denote, so up to normalization and factorial, v, k1, kn, and plus other terms, other monomials. Okay, and this coefficient is called mixed volume of convex bodies, k1, kn. And this is a very classical object with a number of remarkable properties. And some of them I'm going to list now. They will be either directly relevant to the talk or just something good to know. Switch. Yeah.
Thanks. Is it appropriate to ask for a simple example in 1 or 2 dimensions?
Okay, I will say something now. Okay. Yeah. So properties, basic properties. So if you consider mixed volume of body K with itself taken n times, repeat the same convex body, you just get volume K. If you consider so the okay, answering your question. K with Euclidean ball B, Euclidean unit ball. Then this is equal up to normalization. Maybe it should be multiplied by 1/2. I don't quite remember. Maybe 1/2, but maybe without it. Area of the boundary. If K is full dimensional, it is area of the boundary, essentially. This is just an example. Other general property that mixed volumes are necessarily non-negative. It requires a proof. It is not immediate, but it is not something very hard. And there is monotonicity property with respect to inclusion. If you have two n tuples, K1 is contained in M1, Kn is contained in Mn, all of them are convex bodies, then mixed volume of smaller bodies is smaller than mixed volume of larger bodies. Okay.
If the inclusion is strict, then the inequality is strict also.
This is more complicated. No. If the bodies are full dimensional, then I think it is true. Yes, it is true for full dimensional bodies, but otherwise it is not. Doesn't have to be true. And another already non-trivial property and very classical is Alexander-Fedherr inequality. It says the following: mixed volume of A, B with C1, Cn minus 2, all of them are convex bodies, squared is greater or equal than mixed volume A, C1, Cn minus 2, V, B, B, C1, Cn minus 2. Okay, this is a very classical inequality, and there was, especially recently, a lot of work to study equality cases. It was known for a long time, for example, if all bodies are full dimensional with sufficiently regular boundary, positively curved, then this for inequality is satisfied if and only if B is commutative of A up to translation. But say for convex bodies having less regularity, like convex polytopes, there was very recent work due to Schenfeld and Van Handel when they studied equality cases for polytopes. Okay. Now I'm going to formulate some new inequalities satisfied by mixed volumes. And let me introduce a little bit more notation. So I will consider three embeddings, iota 1, iota 2, and delta from Rn to Rn cross Rn, which is R2n. Delta is just diagonal embedding. Iota 1 is just embedding with respect to the first coordinate, and iota 2 embedding with respect to the second coordinate. Oh, sorry, I forgot to mention one more property of mixed volumes, which I will need. Sorry. Let me go back one step. So continuity with respect to all arguments in the Hausdorff metric. V K1 Kn is continuous in K1 Kn with respect to Hausdorff metric. It will be important in a little while. Okay.
It'd be worth mentioning also another example of a geometric quantity other than the volume and the surface area that arises as these mixed volumes, just to give people the idea of the richness of the subject. There's some
if you have mixed volume of convex body K taken, say, I times with Euclidean ball taken n minus I times, this is just abbreviation. Okay? Then it is proportional, for example, to averaged volume of projections of K to all I-dimensional linear subspaces. Or equivalently, it is proportional to averaged section by all n minus I-dimensional affine subspaces. But if you take mixed volume not with both, but with something else, it is more tricky to define, to compute. There are, in some cases, some formulas, but it's more tricky to compute. But these are called intrinsic volumes of normalization. Okay. Okay, and now let me formulate the main results, the new inequalities.
You use that eraser. This one. This one is not good. Well, I'm switching it. Okay.
Theorem 1, which I proved 21. So let the dimension is at least 2, and let we have n-1 convex bodies in Rn, and let B be the unit Euclidean ball. Then mixed volume of iota 1 A1, iota 1 AN, iota 2 A1, iota 2 A n-1, sorry. Comma, diagonal embedding of Euclidean ball taken twice is greater than or equal. Very similar quantity, but these bodies are reflected with respect to the origin, namely iota 1 A1, iota 1 A n-1, minus iota 2 A1, minus iota 2 A n-1, delta B taken twice.
I think that n+1 should be n-1, no? You have an n+1.
No, it's n-.
This?
Yeah, n-1.
Yes, it's n-1.
I suppose.
Okay.
But then, sorry, cannot you just repeat it and get equality?
Sorry.
Does equality follow from this?
Equality?
If you just apply it twice. Oh, no, because they're different sets.
Yes. So these inequalities, also I talked to quite a few experts on geometric inequalities. This inequality looks new, except on the plane. So by the way, pay attention that here all bodies are n-dimensional, including the Euclidean ball. N-dimensional, but all of them are embedded into 2n-dimensional space, and these mixed volumes are 2n-dimensional. And
so if these are centrally symmetric, then it's just identity. Is that right?
No.
No.
It is equality. If all bodies are centrally symmetric, then we have equality. So for symmetric bodies, it is not interesting.
Can you remind what does it mean minus?
Sorry?
Minus. What does it mean?
Reflection with respect to the origin.
I see. Natural defined.
Okay. So when n is equal to 2, these inequalities are equivalent to the following one. that mixed volume of A minus A is greater or equal than mixed volume of A, which I remind is just two-dimensional volume of the body. And this inequality is not something new. It is very well known. And it is essentially follows from much stronger inequality than this. Brun-Minkowski follows. And I will not state exactly what is Brun-Minkowski, but it is something very well known to experts. But already in R3, in three-dimensional space, this inequality seems to be new, and I don't know how to relate it to something familiar, whether it can be deduced somehow from Alexander Fenfield or not. It is not clear. Okay, this is first main result, theorem one. Let me state another new inequality. Theorem two. I proved in the same paper. Again, the same assumptions. Let n is at least 2. Let a1, n minus 1 convex bodies in Rn. B in Rn, like previously, Euclidean unit ball. And the following inequality is satisfied. So the left-hand side of this inequality is just sum of these two expressions. So I will rewrite the sum. I1 A, I1 A, n minus 1, I2 A, 1, I2 A n minus 1 delta B taken twice plus mixed volume I1 A1 I1 A minus I2 A1 minus I2 A minus 1 delta B. And this is the left-hand side, and it is less than or equal the following quantity, gamma n, certain constant, which I in a minute will comment what it is, times mixed volume of A n minus 1 Euclidean ball square. I will say what gamma n is. But first, pay attention that in the left-hand side, so all bodies here are again n-dimensional. But in the left-hand side, both mixed volumes are taken in R2m because all these bodies are somehow embedded into R2m. But in the right-hand side, we have mixed volume in Rm, in the usual sense. So where gamma n is such a constant that equality here is achieved for when all convex bodies are Euclidean balls. I don't know to write down gamma n explicitly, Okay, but this inequality could be considered as some new as a perimetric property of the Euclidean ball, for example. And again, there is a question whether this inequality can be related to something familiar. And I can do it, or I know it only on the plane. So in dimension 2, actually, I was explained this by Thomas Wannerer. This inequality is equivalent to standard as a perimetric inequality on R2. So what is standard as a perimetric inequality on the plane is for convex bodies? It says that length of the boundary of convex bodies A is at most some constant like 2 root of pi, if I'm not mistaken, volume of A square root. In other words, it says that among all plane convex bodies of given area, a ball has shortest perimeter. But already in our
what was this result of Wannerer?
what? It is observation, essentially, that this inequality is equivalent to standard as a perimetric inequality.
So when was it? When was this? When did Wannerer prove this?
What?
What did it say that Wannerer?
Wannerer, yes.
When did he prove it?
When? Well, he told me this privately,
Ah.
and well, I mentioned his remark in the paper with the reference. He did not publish. This is observation. Okay, these are
No, wait a second. So what did he prove? Oh, he proved that the standard inequality is equivalent to this.
Yes, yes.
That's what he proved.
Right. Okay. Now I'm going to leave all these inequalities and to explain some kind of theory and developments and valuation theory which stay behind these two results. In particular, the new idea, the recent idea in valuation theory goes back to Jan Koterbate, who discovered Hodge-Riemann type inequalities on the space of valuations. And this I will explain in generality necessary for this inequality. Okay. So okay, so let me start with some. Okay, it will take me some time to state Kotebate's result, his idea. It will take me time because I will need to build some setup, to develop some theory valuations, and to introduce necessary structures and valuations necessary to, in terms of the structures, Kotebate's theorem is formulated. So, definition. Functional. Okay, so maybe I will do not use this. Okay, let's so I will denote by V, not Rn, but I prefer better to denote Rn by V, just n-dimensional real vector space. This is instead of Rn. and K of V, the family of all convex compact subsets of V. So definition. A functional, scalar valued functional on convex bodies is called valuation if it has the following additivity property. Phi of A union B is equal to phi of A plus phi of B minus phi of the intersection whenever A, B, and the union are all convex bodies. Okay. Next definition. Valuation is called continuous if it is continuous in the Hausdorff metric. And one more definition.
So
Okay.
V is in a product space. It's not a vector space. You need
It is a vector space. I don't need metric, but
how
different. Yeah, right. You're right. Let me comment on that. If you choose Euclidean metric, it induces a Hausdorff metric. But different choices of Euclidean metrics induce different Hausdorff metrics, which are equivalent. The topology is the same. So, of course, you are right. It is not metric, but topology. But Hausdorff topology, maybe it means something else. This sloppy terminology. Right. Actually, I don't need metric to define continuity.
Is it important that it's complex valued, or is it just too real valued?
Yeah, it is not important. Some people prefer to consider real valued valuations. So evaluation fee is called translation-invariant. If phi of just on translates of convex body takes the same values for any convex body K and for any translate X. And we will denote by V the space of all translation invariant continuous valuations. It is certainly a vector space, linear combinations of such valuations are such valuations. And moreover, let me mention that here equipped with the topology, the topology of uniform convergence on compact subsets of script K of V, while V is, in fact, a priori it is just Fréchet space, but in fact one can show it is a Banach space. Okay. I will need this topology a bit later. So this space of translation-invariant continuous relations is, again, very classical space. There is a big literature about it. It was studied quite a lot. And I will need to mention some basic properties of it. First of all, let me mention some examples of valuations. All examples I will mention are quite typical, completely typical, and will be relevant for the rest of the talk. First, the big measure is continuous translation-invariant valuation. Second, so-called Euler characteristic. Chi, it is also translation-invariant continuous valuation. And I remind Euler characteristic of convex body, it is just one, something very simple. This convex body. Third example is more general. So fix convex body A and define phi of K volume of the Minkowski sum. So it is not hard to show. It requires some little argument that phi is translation-invariant continuous valuation. And a fourth example uses mixed volumes. Phi of K is mixed volume of body K taken I times with some fixed convex bodies A1, A, n minus I. Fixed. So this phi is again continuous translation-invariant valuation. Okay. Next notion which I will need about basics. Definition. Valuation phi is called I homogeneous. If phi of lambda k is equal to phi lambda to the power I phi of k for any convex body k and any positive lambda or negative lambda on any commodity. For example, it is not hard to show that this mixed volume when body k is taken I times is I homogeneous. For example, this example has no degree of homogeneity. Euler characteristic is zero homogeneous, and volume is n homogeneous. Okay, and now there is the following important, I will use a notation while I is the subspace of I homogeneous valuations in val V. So it is a linear subspace, closed linear subspace. And now there is the following very important result of Macmullen. 77 approximately. That the space of all translation-invariant continuous valuations is a direct sum where I from 0 to n is dimension of vector space V of this I homogeneous subspaces. So in particular, degree of homogeneity in this case is necessarily an integer between 0 and the dimension of V. And let me give you some information, relevant information for this talk. What is known about these subspaces? So first of all, please. Valuations on R1, it is easy to describe. It is just two-dimensional space spanned by the Euler characteristic and volume, Lebesgue measure. Now let's consider higher dimensions. It is known and easy to see that valuations homogeneous of degree 0 are all spanned by Euler characteristic, and this is very easy. It is in particular one-dimensional space. Valuations of maximal degree of homogeneity are all spanned by volume. This is due to Hadwiger. It is non-trivial statement. Other summands, all of them are infinite dimensional. And let me just mention, without going into technical details, then val m-1 can be described explicitly. But I will not give the description. Due to McMullen. Okay, I will need also further decomposition. So we have here decomposition with respect to degrees of homogeneity, but also we will need decomposition with respect to parity. Val I is val I plus even valuations and val I minus. So valuation is called even if phi of minus k is equal to phi of k, and odd if phi of minus k is equal to minus phi of k as usual. So we have this decomposition with respect to degree of homogeneity and parity. Okay. These are very classical space. And now the next step is to introduce certain dense subspace of smooth valuations, which is less classical. And on this dense subspace of so-called smooth valuations, we will have a structure, product structure, which is necessary to formulate this Hodge-Riemann type result. Okay, so in order to introduce smooth valuations, let me mention that the group of linear invertible transformations acts on val V. Naturally, G phi of body K is equal to phi of G minus 1 K. K is any convex body, G is a transformation, phi is a valuation. And definition. Actually, this definition is much more general than I'm going to say. It's just it comes from representation theory for representations of finitely groups. So, but I will specialize it.
Please switch the boards.
Okay. Evaluation field is called smooth if the map from the group to this Banach space of valuations given by phi, G goes to G acted on phi is C infinity differentiable. Yeah. So this is a Lie group. This is a Banach space. So this should be infinitely differentiable. And I will denote by val infinity V smooth valuations. Yeah, it follows from very general and relatively easy results from representation theory that smooth valuations is a linear subspace linear and dense. What is important also that it is dense. Moreover, it has some canonical Fréchet topology, which is stronger than topology induced from val V. I will not describe it explicitly, but I somehow use it as a black box. But of course, let me first mention a few examples. Maybe I will of smooth valuations. No, of course, volume and Euler characteristic are smooth. These two examples don't have to be smooth, but they will be smooth if all these bodies A and AJ are assumed to have infinitely smooth boundary and positive Gauss curvature. Then these valuations will be smooth, and for many purposes, it is sufficient. Not for all, but for many. An advantage of having this space of smooth valuations that it has an algebra structure which I will summarize in the following theorem, which I proved in 2004. Well, first of all, val infinity V has a canonical bilinear linear continuous. In this Fréchet topology, which I didn't describe, map old product. It is going to be a product val infinity times val infinity, which is uniquely characterized by the following property. If we consider the following two examples, phi of something, phi of k, it is volume of k plus certain fixed convex body with smooth boundary, etc., and another similar valuation. Then phi times psi, the product in sense of valuations is equal to on the body k volume. So here it is volume on V. Here we take product measure on diagonal embedding of K plus A cross B, direct sum. So it turns out it is a non-trivial result, which I proved long ago, that linear combinations of valuations of some such form are dense in the space of valuations, and hence this property characterizes product uniquely. But to prove existence, it's another step, which I don't explain. With this product, smooth valuations becomes a commutative associative algebra with unit, which is the Euler characteristic. Product is compatible with Macmillan's decomposition. And val I times val j is equal to val, no, smooth, of course. I plus j, the degrees of homogeneity add up. It is an easy property. And the last property I would like to mention is Poincare duality, infinite dimensional Poincare duality. Duality. If we have non-zero valuation phi homogeneous of degree I, then there exists valuation psi of complementary degree of homogeneity, such that the product is not zero. Which is valuations of maximal degree of homogeneity. All of them are proportional to the Lebesgue measure.
So this product doesn't extend to the space of all valuations.
All women.
You have smooth valuations inside all valuations.
No. I don't know if it is proven rigorously, but it seems it's not. Okay, and now finally let me state Hodge-Riemann type theorem, which is a very recent development in valuation theory. And it was initiated by Hodge-Riemann. Okay. This is two.
Yes,
good.
it's fine.
Hodge-Riemann type. I will denote by V1, so-called first intrinsic volume, which is up to some standard normalization, which I don't write down. It's mixed volume of body K with Euclidean ball taken n-1 times. So V1 is smooth one homogeneous valuation. Now I fix again Euclidean metric. Now I have to fix Euclidean metric. Next, I consider valuations, smooth valuations, homogeneous of degree I, and consider primitive subspaces, plus or minus, depending even or odd, plus or minus, primitive, which is valuations, I homogeneous valuations, and I should say, less than half, even and odd, respectively, I homogeneous, such that phi times V1 to the power n-2i plus 1 is equal to 0, where the product is given in terms of valuations, in terms of this theorem. This product belongs to val n-i plus 1. So it should be 0. How one defines primitive subspaces. And for phi on val I, we define Hermitian form. Q of phi, Hermitian form, -1 to the I, phi times complex conjugation of phi times v1 to the power n minus 2. So it is, so if you add up degrees of homogeneity, this is product in sense of the theorem, you get valuation of maximum degree of homogeneity. All of them are proportional to volume, I remind. And there is the following theorem, which I will comment in a minute to give credit correctly. So if phi is primitive, so minus either even or odd and non-zero, then the following inequality holds: plus or minus u of phi is positive. Now let me mention that even result was proved by, so the whole idea to use to get Hodge-Riemann results for valuations is due to Cotter, and he himself proved it in this form 21. Sign minus, he proved it jointly with Vannerer in 22. And now, how all this is related to inequalities, which I stated in the middle of the talk?
So what is phi bar? Is the complex conjugate?
Yes, complex conjugate. If we take some specific linear combination of mixed volumes, which are examples of valuations, specific linear combination has to be chosen to get primitive valuation in sense of this definition, and computes this. And if we compute this product explicitly in geometric terms, in terms of mixed volumes, then we get these two theorems which I stated without using language of valuations. Okay. Okay. So okay, that's all.
Okay. Thank you very much.
I enjoyed your talk.
Time for one quick question, if somebody wants. No, well, thank you very much for very clear.